I will introduce our speaker today. So we have Fumihiro Naokawa from the University of Tokyo in Japan. So he's a PhD student, so he's finishing his PhD, and he's interested in cosmology and observational astronomy. So he also has a keen interest in amateur astronomy in spare time. And he's actually hoping to come here as a postdoc next year, as a visiting postdoc from Japan, to work on trying to probe basically dark energy using radio galaxies. And he'll talk about this today among other things. So please take it away.
Thank you, and good afternoon, everyone. Thanks for coming. As he explained kindly, I'm Major Fumihiro, soy de Nara Prefectura. Soy de Nara Prefectura, Japan, Nara cerca de Kyoto, estudiante de la Universidad de Tokio. Solo un poco español. So thank you very much, and please. So before the main topic, let me introduce a little. I love some sports. I understand it's not appropriate to say I'm a Barca fan here, but actually I also love football and Formula One, and as he said, I love amateur astronomy. So I'm doing some amateur astronomy with this small telescope and also iPhone, and I'm sticking to using iPhone. And I first began with this small telescope, but I recently used an unused observatory in the University of Tokyo, and I improved my technique with my iPhone for higher angular resolution from this Tokyo sky, and higher sensitivity, and not only the galactic sources, but also the extragalactic sources, such as the quasar. And this is detected by my iPhone, and I say this is the oldest photons, world record of oldest photon, which directly hits the CMOS sensor of iPhone. And supernovae 3 years ago, and I established some method to do a photometry with iPhone, and I made a light curve of supernovae with my iPhone and the telescope. Let's move on to a science topic, a real science topic. I'm interested in cosmology, and this is today's topic. And I'm also doing I have been working on time domain astronomy, especially using CMOS sensor. This is not the iPhone CMOS, but it's a professional use CMOS, especially for exoplanets or M-dwarf superflare. And recently integrated these two interests and making a new project, measuring the geometric distance of Andromeda galaxy. This is also for cosmology. Today, because of the lack of time, I prepared only one slide for that, but this is for Hubble tension. Our project is now doing to remedy the situation where we have only several so-called anchor galaxies to calibrate the selfies of the TLGB in the local distance ladder, which is critical to make the robust discussion about Hubble tension. And yes, I have already 17 half nights of Subaru nights. Subaru HSC night has been awarded, and I went to Hawaii and gathered the data. And I'm also doing this project by my hand. But my main project is doing cosmology, especially so-called cosmic birefringence. My motivation of this cosmic birefringence is this is a recently reported very tantalizing signal from reanalysis of Planck and Dublin map CMP data, especially its polarization. And I explain later a little, but if this signal is real, that might be the signature of the new physics beyond the standard model. But there are several challenges of this observation, so now I'm interested in the establishment for the independent test of this signal without using CMB, especially using radio galaxies by radio surveys. So before talking about the dedicated contents about that, let's briefly introduce what is cosmic birefringence. This is a all-sky intensity and polarization map of CMB. Maybe you are familiar to this map if you are not in the field of cosmology. And this is observed by Planck. And when talking about cosmic birefringence, only the polarization direction is important. And for simplicity, let's focus on the limited area like this. And this is the schematic pictures. And as you know, without thinking about the Faraday rotation, the polarization directions of CMB photons, CMB photon can keep its polarization direction during its propagation. But in the special cases, the polarization direction or the polarization surface can be rotated to the same direction by same degree simultaneously across the universe. So these rotations causes a situation where the polarization map, which we can observe today by Planck or W map, becomes different from the original one at the last scattering surface. So this is so-called cosmic birefringence. And since the rotation happened to the same direction, that means this universe chooses left or right. That means this phenomenon violates the parity symmetry of the large scale of the universe. So unfortunately or fortunately, it is quite difficult to explain such a parity violating signal within the standard model of lambda CDM or the particle physics. And it is known that, so as you know, we cannot observe the last scattering surface original part, but it is known that the total rotation angle denoted by beta is proportional to so-called E mode and B mode power spectrum of CMB. So by measuring the amplitude of EV power spectrum, we can know the rotation. And surprisingly, recent CMB analysis reported very, very small but non-zero angle of the total rotation angle of the cosmic birefringence. And if this signal is confirmed, as I said, this means a lot. And maybe that is a signature of axion-like particle, and people pay attention. Axion is a new particle beyond the standard model of particle physics, and which can behave as dark matter or dark energy. And because that is an interaction term, so-called Chern-Simons term in the Lagrangian, that can make the simultaneous rotation of polarization. And this is a real signal of EV power spectrum, and Planck W map says 0.3 degree or so. And so this is a allowed region of parameter space of action, which can explain the signal. And so yeah, so difficult thing you don't have to understand today, but so please note that there are two regions, dark matter region or dark energy region for these allowed spaces. And this year, actually, new observation of CMB from Atacama Cosmologist Telescope also reported the consistent signal with Planck and W. So now it is a very hot topic. And so maybe you are not so familiar, you might not so familiar with axion or some kinds of field theory, but so axion field is following the equation of motion called Klein-Gordon equation in the lambda CDM model. And yeah, so that there is a dynamics for the field. And what I want you to understand today is the rotation of cosmic birefringence happens when axion field changes in cosmic history like that. And the total rotation angle of cosmic birefringence is proportional to the total field change, the total changes of the field value of axion. So that makes some problem. So the first challenge of CMB cosmic birefringence observation is when did the rotation happen? So as I said, the total rotation is proportional to the total variation of the field, and always what we can observe is the total rotation angle. So we cannot know when did it happen from the CMB alone. But actually, this is a higher order concern for this observation. So even if we don't know when did it happen, if we really detect the real signal, non-zero signal of EV or the rotation angle, that is awesome. So that means a lot. That is maybe the beyond standard model. However, before that, we have a real problem about the systematics. So in principle, it is really difficult to predict the degeneracy between the real physical rotation of cosmic birefringence by axion or something and the fake rotation by the miscalibration angle of satellite or telescope. And recent observation, recent report from Planck W for ACT did some dedicated analysis to eliminate these systematics using foreground as a calibrator or as an optical simulation. However, it is still relative observation. And maybe Simon's observatory will do some absolute observation within coming 5 years or so. However, if we really want to confirm this signal, maybe we need some independent test of that. So now I'm interested in that. So let's see. If we don't use CMB photons for this signal, what can we use? Maybe astrophysical sources in this universe. But if we want to use sources for this kind of test, there are several conditions. One is, this is most important, but one is that we have to know the intrinsic angle of the polarization for the sources. And also the sources should be cosmologically distant. I name this kind of sources as standard cross. So the question is there any standard cross in the universe? The answer is maybe yes. The one example is radio galaxies. As you know, maybe you are very experts in this field, and so radio galaxy is radio loud AZN, and it's typically accompanies a long tail jet. And so yeah, usually there are strong magnetic field along the jet axis, and when the free action moves around the jet or the magnetic field, that emits the synchrotron radiation with linear polarization. And in this configuration, naively thinking, the polarization direction should be perpendicular to the magnetic field or jet axis. So if we define the position angle and the polarization angle, the difference between chi minus psi should be distributed around 90 degrees. Of course, if we only focus on one sample of AGN, we cannot say anything because there are astrophysical, some turbulence or something. However, if we can collect a mass of sample, the distribution of these two angles is really around 90 degrees, and this is actually observationally confirmed. And so, if action really exists and the cosmic birefringence really happens, only the polarization angle should be rotated. And as a result, the peak of this distribution should be shifted by the rotation angle beta. So we can use this kind of correlation for the test of cosmic birefringence. And actually, this is not my idea. This is a very, very fast, very pioneering test of the cosmic birefringence in the 1990s, 30 years before from the first report from W. and Planck. And this is done by Sean Carroll and George Field and Roman Zecchi, very famous cosmologist or particle physicist. And now I'm revisiting this method because we have a strong hint from CMB. It is different from the situation of 1990. And also we may have a lot of samples of radio galaxies now. And so let's think, so in which cases can we really observe the rotation with astrophysical sources? So maybe this is a little complex, but I'm showing the diversity of the dynamics of action field in cosmic history depending on the mass of the models. And what I want you to understand is when the dark matter cases of action, the field changes predominantly happen in the early universe. These are dark matter cases. Precisely speaking, the mass of action is heavier than 10 to negative 33 electron volts. And as I said, the rotation happens when field changes. So in these cases, cosmic birefringence also happens in the early universe. So we cannot detect with astrophysical sources. However, when the dark energy cases, the mass of action is lighter than 10 to negative 33 electron volts. In these cases, the field changes happen in the later universe. So actually, this is the line that degenerated, but there is a diversity. And so in these cases, we might be able to detect the dark energy or the cosmic birefringence with astrophysical sources. But what I was showing is just the diversity of action field dynamics. So we have to transform to the redshift evolution of birefringence angle. So I calculated them, and surprisingly, though there is a diversity for action field in dark energy cases, actually after transforming to the redshift evolution of birefringence angle, the profile shows unique unique profile. And so I first found this unique profile numerically, but after that I could analytically derive, and I found this unique profile only depends on the dark matter energy, dark energy density of the lambda CDM model. And on the other hand, in the case of dark matter, the dynamics really depends on the mass of the model of action. However, as I said, the rotation already finished in the early universe. So when we only focus on the late universe, the profile should be almost null. So what we have to test with astrophysical sources is to distinguish these profiles. And I forecasted the request sample size of the radio galaxies based on some assumptions. And I found maybe order of 500,000 or 1,000,000 sample is required to test to distinguish these profiles. And the histogram is a recent polarized source catalogues from LOFAR SKA made by Shen. Yeah, so I don't know. And maybe you have a question. So do we have really such a number of samples of radio galaxies? I don't have a clear answer, but fortunately, at least from 2020s, the sample size of radio galaxies is skyrocketing, mainly thanks to LOFAR. And also the polarized sources catalog is skyrocketing, mainly thanks to LOFAR, and also the ASCA, SK Pathfinder, and maybe ASCA Post project is supposed to collect 800,000 samples of polarized sources, and many of them are from radio galaxies. And SKA will improve further. And I tried to do some preliminary tests with LOFAR data. Unfortunately, LOFAR doesn't have any good absolute angle calibration, so we cannot do something with LOFAR alone, but it is really good angular resolution. And with my recent primary data analysis, I found at least we need multi-wavelength observation and multi-wavelength data integrated, and there's pros and cons for every wavelength. But as a sample size, ASCA POSAM is the best. And also maybe we need a power of optical telescope because we have to determine the redshift. And also there is another standard growth in optical wavelength. So yeah, I'm really excited to use all kinds of observation for detecting dark energy. In the most fortunate case, we don't just do the simultaneous confirmation of cosmic birefringence, but also we can detect the fast detection of dark energy in the near future. Yeah, thank you very much.
Do we have any questions in the room for Fumihiro or online?
You are looking for deviation from 90 degrees.
Yes.
How much? 1 degree?
Yeah.
A fraction of a degree?
That is this one. That depends on redshift. At most 0.3 degrees.
And that's large, I think.
Yeah, very, very. So of course, for one sample, we cannot do such a test, such a sophisticated test. But this is a pure argument from the central limits theorem of mathematics. If we collect that, so if we have a uniform sample, we cannot do anything. But if we have some shape of this histogram, and if we can collect enough number of samples, the accuracy of peak position is proportional to the sigma means this outskirт, and over the sample squared of squares sample number squared. Yeah, and I forecasted. Yeah, so how much n is requested, and the answer was about 1 million. But if we can make this outskirts skewed, the sample size will be decreased. Yeah, and so that's my work in postdoc. And of course, there is some systematics for all samples. In that case, it is really difficult. But the unique profile I theoretically calculated has a curvature, not just a constant profile. So in principle, if there is some systematics for all samples, that makes this profile shifted up or down. So in principle, it is possible to distinguish this dark energy profile is existing or not. but it's really challenging. But it was challenging, I think. So is it clear answer for you?
So in cosmology, we know there is a transition redshift from matter dominated universe to the dark energy dominated universe around redshift of 0.67 or 65. But we don't see, and so in later universe when there is a dark energy dominated, so your effect should be dominated, and there should be some kind of jump in this plot.
No.
But why there is no jump and it is smooth? Because coupling will be dominated in the later universe as compared to when in the better dominated universe.
So in cosmic birefringence cases, the action which can explain the dark matter cannot be responsible for all energy density of dark matter because the Broglie wavelength is too long to make galaxies. It's only at most 1%. So if there is a dark matter-like action for cosmic birefringence, so the coupling always happens in cosmic history. But the point is the coupling makes the rotation only when the field value changes. So if there is a matter dark energy transition point around here, there is no jump because the interaction always happens. But just important thing is the changes of the field value of action. So that is not comes from the transition of the energy density domination of the universe. Actually, so for simplicity, I couldn't say anything, but when I calculate the numerical value of this one, I actually included all kinds of energy contribution from action and dark energy and dark matter, and I checked that.
There is one question online. You can unmute your microphone.
Yes, can you hear me?
Yes.
Yes.
Okay, thank you. Yes, thank you for the interesting talk. So, if I understood clearly, the assumption for the observational signature is this helical magnetic field around the jets, and that it should be the polarization perpendicular to the position angle of the jet. There are several factors that can alter this picture. First of all, there are bent jets, right? So that jets are not always straight.
Yeah.
So, and depending on the frequency, the position angle of the jet is changing. Optical depth is another thing. So, optically, the assumption that the polarization angle is perpendicular to the magnetic field holds only for optically thin emission. If you go to lower frequencies in optically thick radio emission, lower radio frequencies, then the polarization angle is parallel to the magnetic field. And also, the helical magnetic field in the jet is something that is somehow confirmed, but the step of the helix is not constrained very well. So it's not always that the helix of the magnetic field is tight around the jet. So my question is, do you take these factors into account from your analysis, or do you expect that they will just increase the scatter of the deviation that you're looking for?
Yeah, thank you very much. So the simple question is, I just did very simple forecast for this paper, but of course, I'm thinking about that and I discussed about that in my paper. So let's back to the slide of the histogram. So as you say, the histogram is not so simple. And actually, this histogram shows one peak in around 90 degrees, but already it is known that there is a sub-peak around 0 degree because there is some, not perpendicular, but aligned cases of polarization and jet. And so, but yeah, so there are plenty of astrophysical deviation and also very complex stories, but can you see me? No?
Yes.
Okay. So yeah. Okay.
Yeah.
So maybe I will use my pointer. No, it doesn't work. So yeah. So maybe my laser pointer. Yeah. So all kinds of astrophysical sources all kinds of deviation originated from astrophysical sources is expected to be included in this sigma. And the point is, if there are so many astrophysical deviations, that should not violate the parity symmetry when we collect the mass of sample from all over the universe. So we can, in principle, take that into statistical consideration. And but that is actually what I will do. So which kind of astrophysical contamination is there, and if whether we can extract from some prior information. Yeah. So, but this test is robust because that can be included in the standard deviation of this histogram, and also the that should not violate the parity symmetry. So if we have some parity violating shift from the expected 90 degrees or 0 degrees about the peaks, that means we should discover something. And if there is a systematics, we can distinguish from the real physical parity violation and the systematical parity violation by using redshift dependence of my profile. Yeah, so thank you very much. Is it clear answer for you?
Yeah, it's clear. Yeah, thank you.
Thank you.
There are some effects that are symmetric, broadening the distribution, and some that are not symmetric. But okay, good luck.
Thank you. Thank you.
Okay. Any other questions in the room?
Well, I have a curiosity. You mentioned before that you need your best target are radio galaxy. I was wondering if you need, for example, FR2 or FR1 radio galaxy, or also a more compact radio emission is enough.
Yeah,
for
so
your analysis.
Prolonged one is maybe better. Yeah, so we are checking from April with Shen, so about every classification of ASEAN, and so what is the population which is dominantly in the outskirts, and what is the population in the really speak around region. That are my work, and please give me the knowledge from ASEAN side about that.
Thanks. Any other question online?
Okay. Any final questions in the room? No? All happy? Well, let's thank Fumihiro again. And he is here for the rest of the day. So tomorrow and Friday, he will be in office 2 to 6. So if you would like to talk to him, yeah, he's available.
Thank you for joining us.